All right, let's just get it out there. Your model sucks. I know. That's harsh. But hey, if you're here, it's probably because you've poured hours, maybe even days, into building something that just isn't working. Well, don't worry. We're about to fix that, and fast.
We've all been there, right? You've done all the hard work. You've cleaned the data, you've picked your algorithm, you've hit train, and this is what you get. That dreaded low accuracy warning. It is one of the most soul-crushing moments in machine learning. You did everything by the book, but the result is just not good enough.
Or you fall into this classic trap. You look at your training scores and they're nearly perfect, 100%. You think, I've done it, I've cracked it. But the moment you show it some new data it's never seen before, it completely tanks. That's not a perfect model. That's a model that just memorized the answers to the test, which makes it totally useless out in the real world.
But what if I told you that you can diagnose pretty much all of these problems in less than a minute? The secret is a simple, powerful visual tool called a learning curve. So it's time to stop guessing, stop randomly tweaking your model, and let's actually see what's going on under the hood.
This brings us to the diagnosis itself. It all starts with understanding the health of your model. And we're going to do that by basically taking its pulse and watching how it learns over time.
Now, before we get to the good stuff, let's just do a super quick refresh to make sure we're on the same page. This is the typical journey, right? You get your data, you clean it up, and you split it into your training, validation, and test sets. Your model learns from the training data, you tune it with the validation data, and then you give it a final exam with the test data. The problems we're talking about today, they almost always pop up in that critical loop between training and validation. And that brings us to this key concept, goodness of fit. Look, this isn't about how well your model did on its homework. That's the training data. This is about how well it performs on the final exam, the new, unseen data it's going to face in the wild. A model with a good fit is one that can actually generalize what it's learned. That's the whole point.
And this is our main diagnostic tool, the learning curve. Seriously, think of this chart as a stethoscope for your machine learning model. By plotting how well it's doing on both the training and the validation data, you can literally see what's happening inside its brain. Is it learning? Is it getting confused? Is it just memorizing? This single chart tells you everything you need to know.
So let's diagnose the first common illness your model can catch, underfitting. This is what happens when your model is just too simple, too basic, to really understand the patterns in your data. And you can see it so clearly here. The data points obviously follow a curve, but our model, that orange line, is trying to fit it with a simple straight line. It's like trying to draw a circle with a ruler. It fails on the training data, and it fails just as badly on new data. If you looked at its learning curve, you'd see that both the training and validation errors are high, and they've just flatlined. The model just gave up. It's not powerful enough to learn.
So, how do we fix it? Well, here's the prescription. The model is too simple, so make it more complex. Add more layers or neurons if it's a neural net. You can also give it better clues by engineering more relevant features. Or you could use a technique like boosting, which cleverly combines a bunch of simple models to make one really smart one. Sometimes you just need to train it longer, or reduce something called regularization, which can sometimes hold a model back too much. The goal here is simple. Give your model more power.
All right, now let's talk about the opposite problem, which is honestly way more common. I'm talking about the overfitting trap. This is where your model gets a little too smart for its own good.
This graph is the perfect picture of an overachiever. See how that orange line hits every single training point perfectly? It hasn't just learned the pattern, it's memorized every little wiggle and bit of random noise. But look what happens when it sees new data. It's completely off the rails. The learning curve for this would show a huge, glaring gap. Your training error would be near zero, but your validation error would be super high.
The cure for overfitting is all about one thing: helping the model generalize. The number one best fix? Get more training data. If you can't, you can use tricks like early stopping, where you stop training the moment its performance on new data starts to get worse. You can also use regularization or dropout, which are clever ways to force the model not to rely too much on any single piece of information. Sometimes you just got to simplify the model. It's all about teaching it the general rules, not letting it memorize the specific answers.
Look, fixing these problems after the fact is great, but you know what's even better? Preventing them from happening in the first place. And that really comes down to having a solid philosophy from the very beginning. And honestly, it's as simple as your ABCs. A, always check your assumptions about the data. Don't just assume it's perfect. B,
Be aware of and actively work to reduce biases, both in your data and in your model's logic. And C, understand and validate the constraints of your problem. Stick to these basics, and I promise you'll save yourself a world of pain down the line. So let's pull all this together. Building a great model isn't about chasing a perfect score in your training set. It's about building something that's robust, reliable, and actually useful in the real world.
This quote right here, it absolutely hits the nail on the head. Underfitting is what we call a high bias problem. The model is just too biased by its own simplicity. Overfitting is a high variance problem. It's way too sensitive and varies wildly with the training data. That perfect sweet spot, the optimal fit, is all about finding that perfect balance. That, my friends, is the real art and science of building models that work.
So, you've used the learning curve. You've balanced that bias and variance, and your model is fixed. That's fantastic. But you know, the real world never sits still. Data changes, patterns shift, what we call concept drift happens. So the final question I want to leave you with is this. Now that your model is ready for today, how do you make sure it's ready for tomorrow? That's a whole other challenge. Thanks for tuning in.